Welcome to BMLabs. Learn clearly, think deeply.
Think of a complex mathematical function as a precision machine. You feed it a number, it follows a strict set of algebraic rules, and it generates a specific result across an infinite landscape. This formula, f of z equals z squared plus 3z plus 1, is a machine that runs flawlessly. You can drop in any complex number you want, and it calculates a valid output. Every coordinate on this plane lights up with an answer. But writing down a string of algebra doesn't actually give you the complete picture. To fully define a function, you also have to map out exactly where that formula is legally allowed to operate. Mathematicians call this operating territory the natural domain. It is the largest possible set of complex numbers where the equation actually makes sense. The problem is, the complex plane is infinite. You could spend the rest of your life trying to list out every single allowed input, and you wouldn't even make a dent. So we have to work backward. Instead of looking for where the math works, we actively hunt for the gaps. We search for the exact geometric locations where the machine breaks down. This formula is the reciprocal function, 1 divided by z. It's our first candidate for a diagnostic check. Because division by 0 is undefined, this formula crashes the moment you feed it a 0. Let's test 1 divided by z squared plus 1. We set the denominator to 0, finding z squared equals -1. The forbidden inputs are positive and negative I. These become literal coordinates deleted from the grid. These algebraic solutions translate to zero-dimensional scars on the plane. The rest of the landscape is perfectly healthy, but these specific points represent empty space in the function's reality. Now let's see a formula dividing z by z plus its complex conjugate. We break the denominator into real and imaginary parts, x plus iy and x minus iy. The imaginary parts cancel out, leaving the condition 2x equals 0. This tells us that the equation breaks down anytime the real part, x, is exactly 0. The y value doesn't even factor into the failure. On the coordinate plane, the condition where x equals 0 defines the entire vertical axis. Because of that one algebraic quirk, the forbidden zone is an infinite line, a chasm that divides the left and right halves of the plane. A single algebraic cancellation just destroyed an entire dimension. The allowed landscape is now split down the middle, separated into two isolated worlds. Let's examine one final structural anomaly. This formula involves the modulus of c, 1 divided by 1 minus the modulus squared. Running our diagnostic, we look for where that denominator hits 0. This occurs exactly when the modulus equals 1. Geometrically, a modulus of 1 traces the entire unit circle. The math works perfectly inside the circle and miles outside of it. The only place the machine stalls is on that razor-thin circular boundary. A mathematical border doesn't have to be an edge you can't cross. It can be an isolated dead zone entirely surrounded by valid, infinite possibilities. We found the isolated points that puncture the plane. We've seen the infinite lines that slash it in half, and we've mapped the closed circles that trap it. But here is a common trap in mathematics. If you only list those broken, forbidden zones, you haven't actually answered the question. A proper domain definition must state the surviving landscape. It's the full, intact set of complex numbers remaining after the failures are removed. Understanding a complex function requires mapping its negative space. We define the machine by the precise geometric scars where it is forbidden to go.
Keep learning with BMLabs. Follow for more simple and powerful lessons.